Hello everyone, this is Dr. Hopkins narrating the next video in our series for Chem 472, and today's video will be about free energy and chemical potential. It's a little bit of a hodgepodge. So we're going to start with the Gibbs-Helmholtz relations, and actually basically what we're going to look at is the temperature dependence of free energy. So we start out with our two defining equations for Helmholtz and Gibbs, and then the derivation of the partial derivative of each of those with respect to temperature at the corresponding constant pressure and constant volume, something we had derived in a previous video. But both of them are minus the entropy of the system. So let's do a seemingly innocent manipulation. So what we're going to do, rather than evaluate the partial of just the Gibbs, let's divide the Gibbs by temperature and then see how that varies with temperature. So we're going to evaluate this partial derivative at the beginning. Now, G over T is a function that we need to use the chain rule in order to derive it or do the derivative. And so we have these two terms in the chain rule, and then we do some substitutions from above, and in the end, it's the enthalpy of the system divided by T squared, or minus the enthalpy of the system. We could do the same derivation for Helmholtz, and we would find it's the internal energy divided by T squared. So we can extend that just to, if we extend it to delta G and delta A, what we're typically after, then this quantity will vary with temperature according to the change in enthalpy over T squared, and this is the change in internal energy over T squared. So now let's further examine the temperature dependence. So if we go back to this slide, now these are they would be slopes of these quantities, but notice it still has temperature in the slope. So let's do the evaluation of delta G over T. So we're going to look at how that changes with a change in 1 over temperature, right? So the inverse of temperature. So we're going to get rid of that negative 1 over T squared, and it ends up being just the enthalpy of the system, or the internal energy when we're talking about Helmholtz. So we could plot the delta G over T versus 1 over T, and the slope of that plot in any position would be the enthalpy of that process. So it's one way to evaluate that. We will extend this when we start talking about equilibrium. Okay, so the second part of this video is chemical potential. We're going to introduce the concept of chemical potential, and this is something that we're going to work through for the rest of our discussion of thermodynamics of systems. So in this case, now we're going to go beyond just a gas phase, right? So we're going to allow our moles to change. So they might change from gas to liquid or liquid to gas. They might change from one molecule to another, such as in a chemical reaction. So we're going to start now thinking a little bit more like a chemist. So in order to do that, we need to introduce these partial molar properties, and we've already done that for one of them. We did this for partial molar pressure, right? Dalton's law. We can do these for all of our state functions. But it turns out the most interesting is for, at least from a chemist standpoint, is for Gibbs free energy. And so we'll expand the Gibbs free energy in terms of a differential equation. We've got VdP minus SdT. That was our standard, what we were dealing with before. But we're going to add in the sum of how does the Gibbs free energy change as we change the number of moles of each of those components times the change in the said moles of each component. So I. So this is our sum of all of our possible components that might be reactants or phases or whatever we're talking about. This quantity is quite a lot to write, so we're going to simplify it as mu sub I, and we're going to give it the name chemical potential. So that means now our differential, in most of the differential equations of Gibbs free energy that we see from now on, will be VdP minus SdT, and the sum of these chemical potentials times the change in the moles of the chemical potential of the component. All right, and so you know from one, we talked about it in the spontaneity, but you also know from general chemistry, biochemistry, that basically a chemical system or any system will make changes to minimize the delta G, right, the free energy, right, including altering chemical identity. So that's the thermodynamic driver behind chemical reactions. But we're going to use chemical potential to predict or represent that tendency. And so if we do a reaction or we do a process at constant temperature and pressure, our differential equation is now just the sum of these chemical potentials times the change in moles. So basically what will happen is a system will minimize the free energy by changing the number of moles of each of the components, and so it's basically going to increase the amount that has the minimum chemical potential, right? Makes sense, as opposed to increasing the amount that has a maximum chemical potential that would be maximizing our delta G. So we're going to go to a point where we have minimal chemical potential. Now, the last thing we're going to talk about is the Gibbs-Duhem relation, which basically kind of establishes this idea that the chemical potential does not change independently within a system. So if we have, and in this case it can be phases, that's probably the easiest way to think about it. For any multi-component homogeneous mixture, we can expand G in terms of the sums of chemical potential N, right? And we can take the differential of that, and we'll notice the total Gibbs free energy is just the total of the partial Gibbs free energy. That's what this component is, sorry. Times the number of moles of each of those components. Kind of like the sum of the partial pressures adds up to the total pressure in Dalton's law. So our differential within these sums is just n d mu and mu dn. So we have our two parts. But remember, this is a state function, so this part of the function is equal to vdp minus sdt, right? So at constant t and p, that's equal to 0, right? Because there's no change to this. So that component is equal to 0. If you want to think about it, the system, if you're not changing the temperature, you're not changing the pressure, it's going to go to an equilibrium. So if we were to think about this as a two-component mixture, the sum of n of 1 times the change in the chemical potential plus the moles of 2 times the change in chemical potential is equal to 0. So that establishes the fact that they cannot change independently. We can't have a liquid phase and it change its chemical potential without also changing the solid phase chemical potential that's there as well. Okay, and that's represented here. So you can see exactly how they must change by this. But basically what it's saying is that the chemical potential is going to stay the same, or excuse me, is not going to change independently in any homogeneous mixture. So until next time.